Good morning. How are you? Before we start with the second part of the data converter fundamentals, I have to make a correction on a slide from last week. This is the definition of the DAC gain error, and what you see here is the output voltage normalized to the VLSB for all input bits set to 1. So this is this value. The next term, this. So this was the first one. The next term is the output voltage for all input bits set to 0. So the difference describes this output voltage difference in terms of VLSB. And we compare this difference to the ideal value here, which is 2 to the power of n minus 1. And what I did last week by accident is that I did not draw the blue line here, but I drew it here. So of course this is wrong. So this is V out for all inputs set to 0. So actually this corresponds to the offset. This I did say, but I wrote it down wrongly, so this is the correct value here. I put the correct slide in the file that you can download, but for information, if you got concerned last time, this is the correct one. Okay. Before I start with today's topic, which is non-linearity in data converter, do you have any questions on the stuff we did so far? If not, I'd like to start with the non-linearity. This was the last slide that I gave you as a motivation last week, and we saw, for instance, if we have not a linear transfer characteristics as the red line, but something that shows kind of saturation, like the blue line. Then if we input a sine with a relatively large amplitude, we see that small values are not or only a little bit distorted, but large values see a deviation from the ideal red case compared to the blue one. And if we look at the output sign of such a nonlinear system, then we see that especially for large values we see a high deviation from the ideal value, and this is the nonlinearity. So what I want to do today is to give you some measures of nonlinearity. How is nonlinearity defined? And then in the second part of today's lecture we will investigate the impact on mixed signal systems. The definitions of the nonlinearity and accuracy terms sound somehow complicated. That's why I give you pictures for all of these definitions to give you an impression how what these definitions actually mean and how you measure the nonlinearity from the converter characteristics. So the first one is the absolute inaccuracy, and let's read the definition of the absolute inaccuracy together. It is defined as the maximum deviation of the actual analog value. So the actual analog value from the ideal one. So as nothing is cancelled out, it includes of course the offset and the gain error. Let's look at these characteristics. The black dots indicate the ideal DAC characteristics for a 3-bit DAC. Then we get a DAC, we measure it, and for instance the values we get is the red curve. So the absolute inaccuracy is the deviation of the red curve from the black one that indicates the ideal values. So the maximum deviation of the actual analog value from the ideal one. So we can define this for each point. So this is actually the absolute inaccuracy. if we want to give a single number as it is written in this definition, then we simply take the largest deviation. Or we can say we define this absolute inaccuracy for each point individually. So for each input value, for instance, 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. For each input value, we get an absolute inaccuracy value. Well, now you might say, interesting, or what we want to do here is to measure the non-linearity. We have seen that there is also offset and a gain error. And these errors are not non-linear. This is errors, yes, but it is a linear error. So if we want to focus on the non-linearity, we can go for the relative inaccuracy, and the relative inaccuracy is defined in the same way. However, first the offset and the gain error are removed, and then we measure the non-linearity in the same way. A quantity that is more common in literature is the so-called integral nonlinearity. And the integral nonlinearity is defined as the deviation of the actual curve from a linear line. So somewhere I wrote this, the integral nonlinearity error is defined as the deviation of each analog value from a straight line. So you might ask, what straight line has to be used? And the easiest thing is to say, okay, I take my first value where all inputs are 0. I take the last value where all inputs are 1. And I connect these 2 points. And this is my reference line against which I measure the integral nonlinearity. So let's take these 2 points, connect them, and we get a curve like this. And the integral nonlinearity now is defined as the deviation from the analog value from this ideal line. So this is the integral nonlinearity. There is other definitions possible for choosing this straight line. Another one is to say, okay, we take our non-ideal nonlinear curve and we find a best fit line into this characteristics. So we try to find a linear function that minimizes in a quadratic sense the error between the linear function and this nonlinear converter characteristics. So this is somehow a regression line. However, this one is harder to find. This is a good definition that you can use if you measure the nonlinearity with a computer tool like MATLAB. When you can do a real calculation, then you can use this regression line. If you have a plot of your characteristics and want to estimate the nonlinearity, the first definition is much easier because you take a ruler, connect first and last point, and simply find the deviation. So we will always use in this course the first definition. However, if you go through literature and if you find other definitions, don't be concerned. This is a marginal difference, and yeah, different definitions are possible, and just check which definition the authors use in order to understand what they want to show. Pardon me? Not exactly. The question is, if I take one or the other definition, does this give the same result? Here you can see in this curve the integral nonlinearity is always positive, so we are always above this reference line. Here not. So obviously here, if we sketch here the same values, they are different. It depends a little bit on the application, which one is better. Marginal differences. So if we look at the integral nonlinearity, then you can see that this is a global measure for nonlinearity. For instance, we start here with a very small value, and then nonlinearity increases, we get further and further away from the green reference line, and here we come back. So this is somehow a global measure because local effects are accumulated. In contrast, the so-called differential nonlinearity looks only at the difference between two subsequent points. So the differential nonlinearity is the deviation of the analog step size from one VLSB. This means if we go, which color shall I use? Okay. If we increase the input by one LSB, so if I go from here to here and say this is plus one LSB, then in the ideal case we should go up by one VLSB. However, at this point you can see that actually the difference is larger. So the analog step is larger than one VLSB. And this is what we call the differential nonlinearity. The difference from one VLSB is the so-called differential nonlinearity. So you can see here the step is slightly larger than it should be, so we have positive differential nonlinearity. Here the same, here of course the same, here also the step is larger than expected. Then at the next point you see here we are by this difference, the step is smaller than expected, so we have a negative differential nonlinearity. The same holds for the next two steps, they are smaller than they should be, so here we have a negative differential nonlinearity. One important property of a DAC characteristics is also the monotonicity. The monotonicity describes that if I increase the input word, then the voltage goes up. If I decrease the input word, the voltage goes down. This is an important property that is called monotonicity, that is in particular important if you have control applications where you use a DAC or later also an ADC in a control loop. An example of non-monotonic behavior would be that we say, okay, we go from this point to the next one, and instead of going up, we go actually down. And then perhaps up again and up again. Then our characteristics would look like this. We go up here, we increase the input, and then we go down, which should not be the case in ideal converter. And then we go up and go up again. So in this region, we have a non-monotonic behavior. So if you talk about differential gain or something like this, then you see that here you get a negative slope, which can be a problem on system level. And we will see that there are circuits realizing DACs that are robust against non-monotonicity. This is circuits where non-monotonic behavior cannot occur, and there are other circuits that are susceptible to non-monotonic behavior. And I will come back to this point when we discuss these circuits next week. One thing that should be mentioned for all accuracy or linearity figures if one value is given in a data sheet, for instance, written integral non-linearity one value, then this is the largest one. It is better and carries more information if you give a complete curve, which means that you define for each point the non-linearity value. But you can find both in literature. In scientific literature, you usually see the complete curve. In data sheets, you often see only the single point. Both is possible. But what you should understand, if you see this, if one point is given, then it's the max value. If a complete curve is given, then yeah, it's clear what it means. Okay, this is figures describing nonlinearity in digital to analog converters. The question is now, how can we define the same figures for analog to digital converters? And the good news is that it is exactly the same definitions. So in the scriptum we have given a definition that holds for both. However, I again give you some pictures that explain you how you should interpret or understand these definitions. Okay, let's read it again. The absolute inaccuracy is defined as the deviation of the actual analog value. So it is important that we always refer to the analog value from the ideal one. So the black curve is the ideal 3-bit ADC characteristics. And now we measure an ADC that we want to characterize, and for instance we get the red curve. So the deviation of the analog value from the ideal one. So we take always the midpoint of the steps. So we take these points that are indicated here. So this is the midpoint of the steps, and the deviation of the actual point, which is here, from the ideal one is this difference. Here we can see it better. It is this difference. Actual analog value and ideal one. This is the actual one, this is the ideal one, and the deviation is the inaccuracy. Again, more often used is the integral nonlinearity, and for the integral nonlinearity we again need this reference line. We can choose either a reference line that connects the very first and the very last analog step. This is what we use here also. Or again, you can say, I take all these points, I compute a regression line and take this one as the reference. Here, for simplicity, we take the one that connects the first and the last point. And now the integral nonlinearity is defined as the deviation of each analog step from the straight line. So if we use our definition, then of course for the first and the last point the error is 0, because we draw this line exactly through these points. For all other points we can define this. We can say, okay, here is my actual value, and the difference compared to this straight line is my nonlinearity error. The same is here, or here. Here it's a quite large one, or here. This is the integral nonlinearity. And then again, we can take all these values, plot them on an axis, and say, for this input value, we have this deviation from our straight line, and this is our integral nonlinearity. Or we can choose the maximum and can give this as a single number. Again, there is a definition of a differential nonlinearity, and the differential nonlinearity is again a local quantity, whereas the integral one is a more global measure for nonlinearity. And the differential nonlinearity is the deviation exactly the same definition, is the deviation of the actual analog step size from the ideal one. So we can look here and say, okay, we go, if we look at this step width, then this is larger than 1 VLSB, so this is VLSB. Here it is a little bit too large, and the difference is what we call the differential non-linearity. So here, for the first two steps, you can see that the differential non-linearity is positive. The step is too large. Then here we can see the step is too small, so we get a negative differential non-linearity. The next one is more or less ideal. And here again we have one which is too wide, so we get a positive differential non-linearity. There will be a tutorial on this stuff to get a little bit familiar with these quantities. But I hope these slides can help you to understand what is actually going on here. And this is, yeah, the verbal description is somehow difficult, but if you look at the slides, I hope you understand that it is a more or less easy thing. One point is the correspondence of what we had in the monotonicity in the field of the ADCs. And there is something similar which we call a missing code. And the missing code occurs if one step vanishes completely. So if the differential nonlinearity at one point is minus VLSB, so if the difference between the actual step and the ideal one is minus VLSB, then one step vanishes completely. For instance, if we look at this step here, which is already quite small, if this step width is reduced even further, then at one point the step vanishes completely, and then we would have something like this. Then this code never occurs. Okay? If you have all possible input voltages, then you get the 2 value, you get this value, you get this value, but you never get this one. Okay? This one does not occur. And this is what we call a missing code, because this code is never visible at the output. One measurement that you can do to identify missing codes is to simply put noise or a random signal to the input of your ADC. Okay? Then you can say, I have a plot where I put the probability of getting a certain value, so a HB, and on the x-axis I put all possible input voltages, V in. And then in the ideal case you should get something like this. No, let me plot it differently. What you input is, sorry. Move this. No, I do it new. We have here the input, and we have here the probability of a certain input voltage. And if we assume that you have a random signal that is equally distributed, then you get something like this. You have an equal distribution from the min and the max value. So then if you look at the output and say, okay, now I plot here the B out and have here the probability for the output, then you should get the same probability for each value. Okay? So you should get something like this. Same probability for each value. However, if one value is missing completely, then, or is very, very small, then this is an indication for this missing code. So this is a so-called histogram test. And the histogram test is something that reveals non-linearity in measurement without measuring a complete characteristics. Because for perfect linear converter, having equally distributed input signal should result in equally distributed output signal. And if the probability of one signal is much larger or much smaller, then this is an indication that the step width here is much larger or smaller. So this is indication for nonlinearity. Okay. If you go back through the last slides and think about what we did here, then this was a linearity definition always based on an ADC or DAC converter characteristics. So what is the problem here? What is missing so far? What is missing so far is all dynamic effects, all noise. So the key point here is how do we come to this converter characteristics? So if you are in the lab and measure the characteristics of ADC, for instance, then you apply a certain voltage, measure the value, increase the voltage a little bit, measure the value again, and increase the voltage, measure the value, and so on and so on. And then you plot all these values. And unfortunately, you never get such a step characteristics because all measurements are a little bit disturbed by noise. So sometimes you get a value that is one too large, one too small, but you get a awful characteristics that does not look like steps, but has several intermediate steps. For instance, if I sketch it here, if you have here your V in, here you have your B out, and you measure each value only a single time, then it can happen. This is here, this is here, this is here, here, here. Then after a while, probability of being high is larger. Then you get something like this. And so on and so on. But you do not see the steps here. So what people usually do is to measure each point not only a single time, but measure each input voltage, let's say 100 times, and then do somehow an averaging. And if you do this averaging, then you end up with your step function. However, this averaging cancels out all noise effects and dynamic effects. So it cancels out some non-ideality, and it is not really what an ADC or a DAC does that is used in your application. So the question is, how can we have a more realistic measurement setup of these converters? One point is also that there is, we will see this in the last part of this course, that there is even some converters that do not have a characteristics such as step function. They provide the ADC functionality, but they do not have really step function characteristics that can be measured in plot. This is all this field of the sigma delta converters. This is converters that work somehow differently, and hence we cannot easily plot a step function for them. So also for these type of converters we need another measure. And for both of these cases we can use this so-called dynamic ADC measurement. The dynamic ADC measurement is a technique where we take the ADC that we want to characterize, and we give this ADC a continuous clock, At the input, we give this ADC a sine function. So this is this A sine omega t with a certain frequency. And then we let it run. So there is this continuous sine, there is this continuous clock, and continuously data is coming out of the ADC. And then we take, let's say, data logger called logic analyzer. This is a device that you have in your lab that you connect to the output to your ADC, and that records a long data stream of output values. So let's assume we have here a device that logs, for instance, 1 million values coming out of your ADC. And then you put these values into your MATLAB environment and do signal processing, which is usually FFT. And then you get a spectrum of these results of the ADC. So my question for you guys is, here you have already a small plot of this. What will you expect in the ideal case that is coming out of your FFT? Here we have a sine, and we convert this for a while with our converter. Yes, so we would expect that there is two directs, okay? One at a positive frequency, one at a negative frequency. If we look at the result, it usually looks like this. So the question is, how can we understand this measurement? Well, the first thing we see is that there is indeed a significant peak. So in this illustration, which is typical for FFT, we look from 0 frequency to half of the sampling frequency. So the second direct you mentioned is symmetrically mirrored at a negative frequency. So it is also there. But we can see here, this corresponds to our direct. This is our test signal. And this is at our frequency omega. So if you go through your materials from your signal processing lectures, then there is the direct and nothing else. Here in the measurement you can see that there is lots of other values here. So I draw an average line here. So any clue what this is? Well, this is exactly why we do this. This is what people call the noise floor. In an ideal converter, there is always noise, so we get also values at other frequencies. So what is this noise from? Of course, this is the quantization noise that each ADC has. And if we assume that the input signal is random enough, or even then the quantization error is equally distributed. So we see this also as a spread over all frequencies. So this is a white noise. And there is also other noise sources, thermal noise, noise in the transistors, and this leads also to this noise floor. It is not always the case that it is white, but quite often. Then we see other spikes coming out of this noise floor. For instance, here, 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 and so on. Here, this one we do not really see, but there is others. And this is the so-called harmonics. You know, non-linear distortion means that even if we have an ideal sign at the input of the nonlinear system, at the output we get a signal that contains 3 components with twice, 3 times, 4 times, 5 times the fundamental frequency. And this is the so-called harmonics. So this is the harmonics that lead to the distortion. So the good thing with this measurement is we see the noise and we see all the non-linearity in terms of harmonics. We see the signal that is coming out. And therewith we have everything that we need to compute a signal to noise ratio. So let me summarize this here. We can calculate from this plot the signal power, because we can take the values that we get from our FFT, we can integrate in this region around this spike, sum up the values here, and there we end up with the signal power. So we get the signal power. We can add up all values corresponding to these harmonic peaks, and therewith we get the harmonic power. Let me write the power of the harmonics. And we can add together all other values. We can integrate over the noise floor. And this yields the noise power. So we have here the P noise. Here we have the P signal. And we have the P harmonics. Therewith we can define our signal to noise ratio as the ratio of P signal over P noise. So this is the power ratio between the signal and the noise power. And again, we express this in dB, so we take here 10 times the log of P signal to P noise. Or we can say, well, so far we neglected the harmonics, we also want to take the non-linearity into account, so we calculate the signal to noise and distortion ratio. This is the same definition, however, now we take also the harmonic power into account, so we have here P signal over P noise plus P harmonics. We can also quantify our nonlinearity by saying, okay, let's compare the signal power to the power of the harmonics. So this leads us to the total harmonic distortion that can be defined as the log of the power contained in the harmonics and so on, compared. Here I express this in terms of the amplitudes to show you that this is all so way to describe this. You can also take the values from the FFT, but we compare the power contained in the harmonics to the signal power. Or if you say I'm mainly interested in one particular harmonic, then you can say, okay, for instance, I take the second harmonic distortion. Here I take only the second one, or third harmonic distortion is also possible. I give you the example for the second harmonic distortion, where we say, okay, this is only the second harmonic compared to the fundamental. impression is that beginners in this field usually have difficulty in understanding the purpose of the signal-to-noise ratio. So do you remember what I explained you about the signal-to-noise ratio and the resolution of an ADC? Sorry. Okay, there I am again. Is there a relation between resolution and signal-to-noise ratio? I gave you already the definition of the signal-to-noise ratio for quantization noise. And this was this equation where we said the signal-to-noise ratio, which was actually not a signal-to-noise ratio, but it was a signal-to-quantization noise ratio. This was defined, or we derived this as 6.02 dB times the number of bits of this quantizer plus 1.76 dB. So what this equation says, an ideal ADC without any noise except quantization noise, an ADC that has n bits, can provide a signal-to-noise ratio of 6.02 times number of bits plus 1.76. Now we did it the other way around. We said, okay, there is no ideal ADC. In reality, we always have noise. And we have this dynamic measurement to compute the signal-to-noise ratio. We said, okay, we let this ADC running, we log all the data, we compute the spectrum, and from the spectrum, we compute the signal-to-noise ratio. So we have to reverse this formula and say, what this signal-to-noise ratio, to how many bits this does correspond. So we say, we take this equation and solve it for n, okay? So we say n is given by signal-to-noise and usually distortion ratio minus 1.76 dB divided by 6.02 dB. This means an ideal ADC that has the same signal-to-noise ratio than the one we have measured would have n bits. Okay? So to make clear what this is, we don't write here n, but we usually write enop, which is the effective number of bits. So this is very important definition. This equation says an ideal ADC, then the one we are looking at, which has the same SNR than the one we have measured, would have a number of bits given by this enop. In reality, we always have terminal noise, we have non-linear distortion, we have other dynamic effects, which mean that the signal-to-noise and distortion ratio is worse compared to the case where we have only quantization noise. So the effective resolution of an ADC is usually less than the pure number of wires or the number of bits coming out of the device. And this is really important. You have to learn that the number of wires coming out of an ADC, it does in principle not say something about the resolution of this device. If there is lots of noise, then the LSBs carry only noise information. So the signal to noise ratio and the effective number of bits calculated according to this formula, this is the real resolution that says you how good your ADC can resolve the input signal. And this is the value you have to look at if you look at conference papers, if you look at data sheets. Then don't look at the number of wires coming out of the device, look at the effective number of bits. Or usually people do not give, or often do not give the effective number of bits. Then look at the signal to noise ratio divided by 6, then you know how many effective bits you get out of this device. I will give you an example throughout this course. I have to search for a good one where you see, for instance, that 12 bits are coming out of the device, but effectively only 9 are there. As an example, I try to find such an example. Okay. Then, if you look at this definition, or in particular at this one, the signal to noise ratio is defined as the signal power over the noise power. So obviously, if we use a small sign at the input of our ADC for the test, then the signal power is small. If we use a large sign, then the signal power is large. So obviously, the signal to noise ratio depends on the value of the input signal, of the input amplitude. And hence, even more information is given if we have the signal to noise ratio over the input level. So as I said, a very small sign has a small signal power, and if we increase the amplitude of this input sign, then the signal to noise ratio goes up and up and up and up. At some point it reaches a maximum value, which is the so-called peak SNR, and actually it is this peak SNR that we use for the computation of the effective number of bits. And after this peak SNR, we usually fall down rapidly. And then you can see that beyond this peak SNR, this device cannot work as an ADC. Here we have simply overloaded the device, so the input is too large. If you reduce the amplitude, then you go down with your signal to noise ratio and go down and down and down, and somewhere the value reaches 0, which means that the signal power corresponds to your noise power. And then it makes no sense to reduce the signal further, because then you measure nothing than noise. And the value of the maximum allowable input that can be used for this device, this value, and the difference to the value where we have the 0 dB, this is what people call the dynamic range of the ADC. So usually the dynamic range is a little bit larger than the peak SNR. Why? Because we have this effect that we drop here. Unfortunately, peak SNR and dynamic range are often mixed up. Difference is usually not so big, but a clean definition is here. Then if you get a curve like this, you have always to ask, is this the SNR that I see here, or is it the signal to noise and distortion ratio? Because if I also consider the distortion, then this makes no difference usually for small amplitudes. here the curve is the same. But if I increase the amplitude further, then the harmonics come into the play. The harmonics start to peak out of the noise floor. So there is a deviation of the SNR and the SNDR curve, and then you usually get something like this. So this is the signal to noise and distortion ratio, and the red one is the signal to noise ratio. And you see here, depending on what you show and what you do not show, you can somehow polish your results and make them look good or make them look worse. So you have to, as a customer or someone who gets such a device as deliverable, you have to look very, very carefully on what you actually get and what people are showing. Okay. What questions do you have? Yes. So, sorry, I didn't get it, that one. Can you speak a little bit louder, please? Yes. You're right. You're right. So, so question was, how can we define the dynamic range like this? Also, we cannot use the device in this region. Well, it is defined like this. So the peak SNR is the more reasonable value to understand what the ADC can really perform. Yes, absolutely. But you have to make really sure. If we have a collapse like this, you cannot use the device here, but you have to adjust your level plan to make sure that this overloading here does not occur in your application. There is ADCs that do not have this effect, but for sure some of them or many of them do have. Or you can also shift this drop a little bit, but then it's a definition. What is your input level, right? You can shift this above the max level, but it's the same. And it's just a shift, and you define this effect away, but sooner or later it will happen. Okay, other questions? Okay. Then I'd like to spend the next half an hour to understand with you why this nonlinearity is so important, why this distortion has an effect on our system. So I will skip this one. The first thing is that I want to always look at a basic nonlinear system that has only third order nonlinearity. Well, you can also use higher order nonlinearity, but then the computation becomes even more complicated, and you will see on the next slides that it is already complicated enough. There is two useful equations that I used for the computation on the next slides. So if you want to go through this material at home and to understand each four-factor in the equations, then you have to use these relations here. So let's assume we have a nonlinear system, third order, described by this equation, and we insert a pure sine signal at the input. Then we have seen the nonlinearity causes harmonic distortion. So at the output, we do not only get this sine signal that we expect, but we also get first a DC component, then a harmonic component at twice the frequency, and a harmonic component at 3 times the frequency. Okay, then you might say, I will filter this out. perhaps I have narrowband system or whatever, I can filter this out. So what happens then? Are you, by filtering the harmonics out, do you get rid of nonlinear effects completely? You do not agree. Why not? Yeah, yes, you consume energy in this harmonics. Yes. This is a good one. You say we have also an impact on the first harmonic, and this is absolutely correct if you look at this term. So from a linear system, you would expect that the gain of the system is always the same. It's constant, independent of the amplitude. If we look at this, then we can say for very small amplitude, we have to consider only the first term. For larger amplitudes, we have to consider the complete 4 factor here. I copied this on the next slide. Here you can see if we look only at this component, if we look only at this component, I cancel the rest so it gets easier. Then we can say if the amplitude is very, very small, then a to the power of 3 is even smaller than a, so I can neglect this. So I get a gain of a1. So I have my system. I put here the a sine omega t, and what I get is a1 times a times sine omega t. Okay? This is for small amplitudes. However, this is not true if my amplitude is increased, because then I also have to take this term into account. And let's assume that the A3 is negative, which is very often the case, which is the case always if I have this saturation type of characteristics that I flatten out for large and small values. Then the A3 is negative. So this actually is the gain of our nonlinear system. I have to put the capital A out, then I end up with the gain here. So this is the gain of the nonlinear system. A3 is negative, so we can say A3 is smaller than 0. But then you see, if the amplitude goes up, the gain goes down. And this also corresponds to what you say, that you put the signal to other frequencies. But even at the harmonic, at the fundamental, there is impact of the nonlinearity, because the gain of the system is going down the more I increase the amplitude. This is what people call the gain compression, and it is often measured in terms of the 1 dB compression point. You can see we increase the amplitude. Here the gain is this A1, but then if I increase the amplitude even more, then this A3 component comes into the play, decreases the gain, and the measure for this effect is the minus 1 dB compression point. What happens if I have two tones, two frequencies, not only a sine omega t, but now we take a A1 sine omega 1 t and a A2 sine omega 2 t. Then we have this awful computation. It is not important that we go through all of these terms, but what is important is that we understand the components that occur. First we see we have a DC component here. Then we get a component of the first frequency and the fundamental of the second frequency, with a huge awful term here and you can see there is also this effect of the gain compression in here. Then we get components at 2 times the 2 fundamental frequencies and 3 times the fundamental frequencies. So far, no surprise. We have the fundamentals. Each fundamental has its harmonics. And then what comes additionally is that these 2 frequencies are also mixed together. So we get the difference of the 2 frequencies, and we get the sum of the 2 frequencies. And also we get 2 times the first one minus the second one, and 2 times the second one minus the first one, and we get also a component like this. For understanding this, I guess it's more easy to look in the spectrum to this. The 2 red directs are the fundamentals. Then we have a DC component, and we have harmonics of these 2 fundamentals. So we have here the 2 omega 1 and the 2 omega 2, the 3 omega 1 and the 3 omega 2. But then we get this mixed product. We get a component which is 1 delta omega below and 1 delta omega above the 2 fundamentals. And there is also a component right in between the 2 second harmonics, and there is components in between the third harmonics here. So we go in with 2 tones and we get all of this out. And the question is, we already saw this gain compression. So we saw that if there is only a single sign and we have non-linearity, then the non-linearity can degrade the gain of this signal. So now there is 2 signs. So the question is, can they disturb each other also? And this is indeed the case, and we will look at this now. By the way, if I look here always at single signs, then this is something that makes the computation easy. Of course, it makes no sense to process in any mixed signal or RF system a pure sign. This is a placeholder always for a signal in a small band around this frequency that we consider. So you can also use these effects and understand these definitions and effects for narrow band signals around these frequencies. So this is, don't be concerned that we only take signs and say, okay, but it makes no sense to have 2 signs beside each other. Look at this as narrow band signals around these signs. Okay. So we said we look at the superposition of these 2 sign signals. Then we might say the amplitude of one sign is much, much stronger than the other one. So let's assume that the amplitude of the second one is much higher than the first one. Then we can go back to this slide and we can look at the fundamentals. And we saw here is the fundamental of the first frequency given by the linear term of the first frequency. Then we have this term that caused the compression. And then, unfortunately, there is a third term that now contains also the amplitude of the second signal. So if we look only at this term, and if we look, or if we ask what happens for the first fundamental, then we can see in this equation we have these 3 terms that I described. We can first neglect the compression term. Let's neglect this one first, and then please note that usually the A3 is smaller than 0. But then what can we see from this equation? From this equation we can see that we have a gain term for the first fundamental, and this gain term sees a compression by the amplitude of the second sign. So if the A2 goes up, the small a3 is negative, then this A2 reduces the gain of the first signal. So at the beginning the second signal has nothing to do with the first one. And in a linear system this would be always separated from the first one because it's at another frequency. But now we see that due to the non-linearity, the amplitude of the second signal reduces the gain that the first signal sees through this system. And this can be even that strong that the gain of the first signal becomes zero. And this is what people call the desensitization, that we make the system insensitive for the first frequency just by having such a strong disturber nearby that the gain of the first frequency is going down. And as the strong signal is disturbing the small one, we call the strong one often a blocker signal. Because due to the high amplitude, it disturbs, due to the nonlinearity, the first one so much that the gain seen by the first frequency is reduced to small values or is becoming even zero. This is what people call a blocking of the first signal. It becomes even more difficult if we say, well, the second signal is modulated. So the amplitude of the second signal is not constant, but is varying. Then exactly due to the same effect, we can insert this amplitude for the second signal, go into the same equation, calculation is the same, except that the equations become a little bit more complicated. But if you look at this term, you see again we have this desensitization term that contains now also the modulation. This means if we have a varying signal on a frequency omega 2, this modulation is also seen at the first frequency. Why is this? Well, because we modulate the gain that is seen by the first frequency according to the signal that is modulating the second frequency. And therewith we have somehow a signal leakage from one frequency to the other. Well, this for instance can be an effect if we go through a common nonlinear system with two communication channels, because then the data on one channel is transferred to the other channel and becomes there also visible. Although this is different carrier frequencies, different channels, but the nonlinearity makes a transfer of the information contained in these two data. And this is what people call the cross modulation. So it's more or less all the same effect. If the signal is so strong that it creates its own gain, then it is sorry, I always mix up these words. Then it is, of course, the gain compression. Yes. If it is that one signal disturbs the other one, then it is desensitization. Or if the information from one channel leaks to the other one due to the same effect, then we talk about cross modulation. And this is lots of unwanted effects that we have here, which is purely caused by the nonlinearity of the system. Hence, I hope you see that it is very important to have good measures of nonlinearity, in particular in our mixed signal course for ADCs and DACs. However, these effects, of course, are also relevant for other systems. Okay, so these effects can be seen always if nonlinearity comes into the play. One question for you guys. We said we can characterize the nonlinearity of an ADC or any transfer system by its harmonics. Okay? What happens if the system has a low pass characteristic? So let's say we have here our converter. We go in here with one sign, and we come out here with the fundamental plus harmonics. What happens if this system has somehow a low pass characteristic, which means that we have some frequency selectivity here? What happens then is that we damp here the harmonics with this low pass. So then we measure this device, we look at the harmonics and say, hey, wow, the harmonics are quite low. So the system has to be very, very linear because there is only small harmonic distortion. However, this has nothing to do with the linearity of the system, but it has to do that components at higher frequencies are damped by the intrinsic frequency characteristics of the device. And hence, harmonic distortion is somehow dangerous because as soon as you have this frequency selectivity, you might misinterpret the results. And hence, people came up with another test, which is a so-called two-tone test, and which is also called an intermodulation experiment. Let me go back to this slide. Here we saw if we have two fundamentals, then we get two components above and below the two tones. And the distance is here, if we call this a delta omega, then we go 1 delta omega up and 1 delta omega down, and we have here this so-called third order intermodulation product. If we look at the harmonics here and here, then we might experience this frequency damping. If we look at these two components, then the advantage is that if these two components are nearby, then the frequency selectivity is usually small, and we can really interpret the nonlinearity of the system from these two values. So the point is we have to take a frequency difference that is very small, then these two components are nearby, and the frequency selectivity can be neglected. And this is what people describe in the so-called intermodulation experiment. They put two tones into the system, and they use these third order intermodulation terms to analyze the nonlinearity. Well, how do these components look like? As I already said, the lower third order intermodulation product is 1 delta omega below the first tone, and the second third order intermodulation product is 1 delta omega above the second tone. And this is these two components, and you can see here they scale with the third power of the amplitude of these two tones. If you go back to the slide with all these equations, then you see the fundamentals scale with the first power of the amplitude. Hence, if you have a plot where you increase the amplitude from low values to high values, the fundamental goes up with A. The third order intermodulation products go up with A to the power of 3. Okay, the red curve goes up according to this term. The blue curve goes up, let me go back. The blue curve goes up with this term, at least for small values of A. So we can sketch the blue curve here and the red curve here. And then you can extend these two lines. You can do an extrapolation of these two lines. And at some point they have a crossing. And this crossing is then a measure people are using to quantify the non-linearity of the system. So by using this point here. This is what people call the third order intercept point. Because here at this amplitude, the third intermodulation product would be equal in size to the fundamental. Of course, usually you cannot measure this point because then other non-linearity effects come into the play. But what you usually do is to measure the first part here, the first part here, and then do this extrapolation. And this, by doing this experiment, you avoid that you fall into the trap of frequency selectivity and might assume that the system is more linear than it actually is. Good. By the way, this is typical curves you see for ADC measurements. You often also make such a plot for the harmonics. Then you say have usually your fundamental that scales with A, and then your harmonics are coming up with a much higher power of the amplitude. The third harmonic with A to the power of 3. The fifth harmonic usually starts much lower but comes up with A to the power of 5 and so on. And by having such plots, you can also investigate whether something is going wrong in your circuit or not. Because if any harmonic doesn't scale with A to the power of the harmonic, then something is strange in your design, and you have to search in that direction. Okay, so this was an overview what may happen if we have non-linearity in the system. I hope you feel motivated to build linear ADCs and DACs in order to have a small impact of all these disadvantages effects. Good. One last slide for today, which has in principle nothing to do with non-linearity, but which will be important from next week on, is the number systems. Before I come to this, people often ask me where they can find literature for all these nonlinear effects. One book I really like a lot is this book of Razavi, which is RF Microelectronics. It's very, very good description of all these figures. The other two books are very useful for all these other data converter figures. This is all three references here are very, very good and useful books for that topic. I put this on the slides for you. Okay, number systems. Well, usually we want to process positive and negative numbers. And what you are used to use is usually the 2's complement representation of negative numbers. This is the number system that is most often used in all digital signal processing systems and processors. The 2's complement means that we have, if we have positive numbers, then the most significant bit is always 0, and all the other bits corresponds to a normal binary number system. So we count up from 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on and so on. If we go to negative numbers, then we have to take the respective positive one, we have to invert all bits, and we have to add a single 1. So, for instance, coming from one positive number to the respective negative numbers, invert all bits plus 1. This is the 2's complement representation. Sometimes there is the 1's complement representation. There this plus 1 step is missing. So in a 1's complement system, coming from a positive number to a negative one and vice versa, is just inverting all bits. In mixed signal systems, namely in ADCs, there is often used different number systems. One number system that is often used is the so-called sign magnitude. Again, the MSB indicates the sign of the number. So a 0 means a positive number, a 1 MSB means a negative number, but then all the remaining bits indicate the absolute value. Okay? So all other bits except the MSB are the same for positive and negative numbers. So we have a sign bit and we have an absolute value. This occurs, for instance, if we have a conversion where we first determine the sign, say, okay, is the voltage positive or negative, and then we work only on the absolute value of the voltage. Then naturally we end up with a sign magnitude coding. And if we want to go from the output of such an ADC, for instance, into a processor, we first have to convert this from sign magnitude to 2's complement. Another number system that is often, or that is quite common in mixed signal systems is the offset binary. In the offset binary, we start from the lowest value that can occur, so usually from the largest negative value, as a negative value with the largest absolute value. So from the smallest value, and we count up until the highest value. In this example, our lowest value is -8, the largest one is +7, and we start counting in a binary way from 0, 0, 0, 0, 0, 1, and so on until we end up with the max value. So the 0 crossing between positive and negative values is somewhere in between. In our case, it is here. So this is the reason why we call this offset binary coded. Because let's assume that we interpret this as pure positive numbers, then to get a real value, we have to subtract this offset here. Okay, actually this is an 8. If I have an unsigned interpretation of this, this is an 8. It should be a 0, so we have to subtract 8. Again here, this corresponds to +9. Then I subtract the offset, which was 8. So I have 9 minus 8, and I end up with +1. This, for instance, is +7 minus the offset. So it is 7 minus 8. Then I have here the -1. This occurs very often in algorithms that do actually not see the sign. We will see that this occurs in the successive approximation converters, where the definition of positive or negative signals is somehow arbitrarily chosen, or not arbitrarily, but is chosen somewhere. And then it occurs that if the value is very small, we get the all 0. If the value is very large, we get the all 1s. In between, we get all numbers. And to end up with an appropriate interpretation, we have to subtract this. So, to summarize, offset binary, sign magnitude, very common in mixed signal, not very common in digital signal processing systems that usually use the tooth complement. So you see there is a need to have some conversion between the number systems when we interface a converter that produces offset binary, for instance, to a digital signal processing system. Okay, that's it for today. Next week we start with the digital to analog converter circuits, and the week after, which is I guess the last week before Christmas, we will start with the Nyquist rate analog to digital converters. Thanks a lot. Enjoy your week.